Welcome to the Deep Dive, the show built to deliver the highest leverage insights from complex sources, giving you the knowledge you need fast.
And today, we are tackling a big one. It's the foundational blueprint for a career in quality assurance.
That's right. Today we're undertaking a deep dive into the ISTQB Certified Tester Foundation Level V4.0 certification. And our source material is really the only one that matters for this. The official ISTQB Foundation Level V4.0 syllabus. It's the map. It's the document that defines everything you need to know for the exam. Our mission today is, well, it's to give you a shortcut. We're going to break down the syllabus, but we're not just going to read definitions. We're focusing on the practical application, the insights, and the deep understanding you need for those tricky questions.
Yeah, this isn't just about passing a test. It's about really internalizing the concepts to level up your professional skills. The foundation level, it sets a global baseline. It means everyone, testers, developers, BAs, we're all speaking the same professional language.
And it's the gateway, right? You have to have this certification before you can move on to the more specialized stuff.
Exactly. Whether you want to go into test automation, security testing, or the core advanced levels like test manager, this is step one. You can't skip it.
Okay, so before we even get into Chapter 1, we have to talk about something fundamental to how you should even study for this. The cognitive levels, the K level.
This is so important. It's not just trivia. This tells you how you need to know the material. It dictates your study strategy.
So there are three of them. Let's start with the first one, K1.
K1 is simply, remember, this is pure recall. Flashcard territory. Can you define a term? Can you recognize a keyword? Things like knowing what testware is or the definition of a failure.
Just basic recall. Got it. So K2 is the next step up.
Right. K2 is understand. Now, it's not enough to just remember the word. You have to explain it. You have to be able to compare, contrast, summarize. A classic example is distinguishing between verification and validation. You need to grasp the logic behind the concepts.
And that brings us to the big one, the heavyweight, K3.
K3, or apply. This is where the rubber meets the road. And this is honestly where most of your study time should be focused. K3 questions require you to actually do something with the knowledge.
So not just define a technique, but actually use it.
Precisely. You'll be given a scenario, some requirements, and you'll have to, say, derive test cases using equivalence partitioning. Reading about it won't cut it. You have to have practiced it.
And the syllabus itself gives us a huge clue here, doesn't it? Chapter 4, which is all about test techniques, is packed with K3 objectives and has the longest suggested training time by far.
It's a clear signal of what the ISTQB values most, practical application.
Yeah.
Okay, so with that framework in mind, let's start laying the foundation. Let's dive into Chapter 1, Fundamentals of Testing. The syllabus allocates a pretty hefty 180 minutes of training time to this. It's foundational for a reason.
So let's start at the very beginning. What is testing? I mean, a lot of people coming into QA, they think it's just about finding bugs.
Right, clicking buttons and logging tickets. But the syllabus immediately pushes back on that. Testing is a whole set of activities across the life cycle. It's about evaluating the quality of software artifacts and discovering defects.
So it includes all the upstream work, the planning, the analysis, the design, not just the execution part.
Exactly. And that breadth brings us to a really crucial K2 distinction right away. Verification versus validation. People get these mixed up all the time. Okay, let's break that down. Verification is
checking if the system meets the specified requirements. It's asking the question, did we build the system right? According to the document, does it do what we said it would do?
Okay, so it's very spec-driven. What about validation?
Validation is about the bigger picture. It asks, did we build the right system? Does it actually meet the user's needs? Does it solve the business problem in its real-world operational environment?
So you could, theoretically, have a system that passes verification perfectly. It meets every single line in the requirements document, but still fails validation because the requirements were wrong to begin with. That happens all the time. The business need changed or the initial analysis was flawed. That's why you absolutely need both. They're two sides of the same quality coin.
To really understand where testing fits, we need to talk about what the syllabus calls the failure chain. This seems critical because the terms are very specific. They're not interchangeable.
Not at all. And you'll definitely see questions that test this. It all starts with a person. A human makes an error, a mistake. A developer is tired, an analyst is rushed, whatever the reason.
Then that human error leads to a flaw in an artifact, like the code or a requirement stock.
And that flaw is what we call a defect. You can also call it a fault or a bug. It's just sitting there dormant in the system.
Okay, so we have the error, which causes the defect. What's next?
Next, the code containing that defect has to be executed.
Yeah.
And if it's executed under just the right conditions, a specific input, a certain sequence of user actions, it may result in a failure.
So the failure is the thing the user actually sees. The observable deviation from expected behavior, the error message, the wrong calculation, the crash. That's it. And then, after the failure, there's one more step: finding the root cause. This is the deep, fundamental reason the original human error happened in the first place. Like, maybe the team lacked proper training or the development tools were inadequate.
Exactly. And the syllabus is very clear here. Root cause analysis is a non-testing activity. Its goal is process improvement, not software evaluation. That distinction really helps clarify the difference between testing and debugging then.
It's the perfect separation. Testing is the activity that triggers the failure through dynamic testing, or finds the defect directly through static testing. The goal is detection.
Whereas debugging is what happens after detection. It's the developer's job usually.
Right. They have to reproduce the failure, diagnose what's causing it, find that defect, and then fix it. Debugging is about analysis and repair. Testing is about discovery.
It's worth pointing out how static testing short-circuits this whole chain, right? Oh, absolutely. When you're doing a code review, a form of static testing, you find the defect directly in the code. You don't need failure to see it. You bypass that entire expensive execution step, which proves the value of early testing right out of the gate.
Speaking of principles, this chapter lays out the 7 testing principles. This is a required K2 objective, and they're basically the universal truths of QA.
They really are. If you understand these 7 points, you understand the why behind almost every testing strategy. Let's start with number 1. Testing shows the presence, not the absence, of defects. This is the philosophical core. We can never prove a piece of software is 100% bug-free. We can run tests, find and fix bugs, and increase our confidence that the system is high quality. But we can't prove perfection. It's a confidence-building exercise, not a mathematical proof, which flows directly into the second principle. Exhaustive testing is impossible. Unless your program is incredibly simple, you cannot test every single combination of inputs, preconditions, and user paths. It's computationally impossible.
And that's why we need the techniques we'll talk about in Chapter 4. We have to use smart strategies and risk-based prioritization to focus our limited time and resources effectively. Absolutely. Principle 3 is the one that gets management to listen. Early testing saves time and money. The classic cost of defect curve.
Exactly. Finding a defect in a requirements document costs pennies to fix. Finding that same defect in production after it's caused a major outage and data loss, that can cost millions. The cost escalates exponentially the later you find it. Okay, principle 4. Defects cluster together. This is the Pareto principle in action, the 80-20 rule. You'll often find that roughly 80% of the defects are found in about 20% of the modules.
So as a tester, your job is to find those complex, buggy hotspots and focus your efforts there. Look at the defect history.
Right.
Next, principle 5, tests wear out. This is sometimes called the pesticide paradox, the idea that if you keep spraying the same pesticide, the bugs eventually become immune.
Same with tests. If you run the exact same set of manual tests over and over, they'll stop finding new defects because the developers have fixed everything they were designed to catch. You have to constantly evolve and update your test cases.
The big exception here, though, is automated regression testing, where the whole point is to run the same test repeatedly to make sure nothing has broken. A very important distinction. Okay, principle 6. Testing is context dependent. You wouldn't test a simple marketing website the same way you'd test the software for a pacemaker.
Of course not. The context, the risks, the industry regulations, the technology stack, the development model, all of it dictates your test strategy. There's no one-size-fits-all approach. And finally, principle 7, which links back to our earlier discussion, the absence of defects fallacy. This is a huge one. It says that finding and fixing lots of defects doesn't help if the system is unusable and doesn't meet the user's needs.
It's the validation problem again. You can have a perfectly verified, bug-free piece of software that is completely useless because it solves the wrong problem. You have to test for what the user actually needs, not just what's written in the spec.
You got it.
So these principles guide the formal test process. The syllabus breaks this down into 7 core groups of activities that happen in some form no matter what development model you're using.
It always starts with test planning. This is where you define the objectives, the scope, the overall approach. You figure out what you're going to test and how. Without a plan, you're just improvising.
And running alongside that is test monitoring and control.
Right.
Monitoring is the data gathering part. You're tracking metrics. How many tests have we run? How many defects have we found? Control is the action part. You see the plan is deviating from reality, and you take corrective action. Maybe you need more resources or you need to adjust the schedule. Then the deep technical work begins with test analysis.
This is where you take the test basis, the requirements, the user stories, and you analyze them to figure out what to test. The output here is a prioritized list of test conditions.
And from what, we move to how with test design.
In test design, you take those high-level conditions and flesh them out into detailed, concrete test cases. You select the right techniques, define the specific inputs and expected results, and figure out what test data you'll need.
Next is test implementation. This sounds like the setup phase.
That's exactly what it is. You're getting everything ready. You create the automated scripts, you organize test cases into test suites, you acquire the test data, you make sure the test environment is stable.
So that when you get to test execution, you can just focus on running the tests.
Right. Execution is the dynamic part. Run the tests, log the results, compare the actual outcome to the expected outcome, and log any differences as defects.
And finally, when it's all over, we have test completion.
This happens at the end of a milestone or a project. You verify that your exit criteria have been met, you archive all your important test assets, you hold a lessons learned session, and you write the final test completion report.
All of these activities produce artifacts, and the collective term for them is testware. You have to know those for K2. So what are some key examples of testware?
Basically anything produced by the test team. The test plan itself, the risk register, the detailed test cases, the automated scripts, the execution logs, the defect reports, and that final completion report. It's all valuable intellectual property.
And the syllabus emphasizes the importance of traceability, linking all this testware back to the original requirements. Why is that so powerful?
It's your safety net and your reporting tool. If a requirement changes, traceability tells you instantly which tests you need to update. That's impact analysis. And it's the only way to objectively measure coverage. You can say with confidence, we have test cases that cover 95% of our high-priority requirements. Without traceability, you're just guessing. Okay, now that we have those fundamentals down, we can zoom out a bit and see how testing fits into the bigger picture of the software development lifecycle. That's Chapter 2, and the syllabus suggests about 130 minutes for it.
Right, so projects can follow different models. You have your classic sequential models like waterfall, and then the more modern iterative and incremental models like agile. How does that choice really change things for a tester on the ground?
It changes everything about the rhythm of your work. In a sequential model, testing is a distinct phase at the end. You get this big handoff, and it's the first time you're seeing the software. This, by definition, violates the early testing principle.
And in an iterative model,
Testing is happening constantly. In every single sprint or iteration, you're doing component tests, integration tests, system tests, static and dynamic testing, all in parallel with development within these short cycles. It demands constant communication and much lighter, more flexible documentation.
but the syllabus makes a point that some good practices are universal no matter the model.
Yes. The main one is that for every development activity, there should be a corresponding test activity. So if the dev team is writing the architecture design document, the test team should be analyzing it for risks right then and there. You don't wait for the code.
This sounds like the formal term for this is the shift-left approach.
That's exactly it. It's taking Principle 3. Early testing saves time and money, and making it a formal strategy. We are deliberately moving quality assurance activities as early in the life cycle as possible.
So give me some concrete examples. What does shifting left look like in a team?
It means doing static testing, like reviewing requirements and code, long before anything is executed. It means adopting test-first approaches, where you actually write the test cases before the code is written.
And it also means using things like continuous integration or CI, right?
Absolutely. With CI, every time a developer commits a change, a suite of automated component tests runs immediately. You get feedback in minutes, not days or weeks. It's a classic shift-left practice.
You mentioned test-first approaches. The syllabus calls out 3 of them specifically for K1 recall.
Right. You have test-driven development, TDD, which is very developer-focused for writing small units of code. Then there's acceptance test-driven development, ATDD, which is more collaborative. Here, you derive tests from the user's acceptance criteria before development even starts.
And the third one is behavior-driven development, BDD.
BDD is like a specialized form of ATDD. It formalizes those acceptance criteria into a very specific, easy-to-read language, the given when-then format, so that business stakeholders can read and understand the tests.
The ultimate evolution of all this seems to be DevOps.
For sure. DevOps is all about culture, automation, and creating these incredibly fast feedback loops, usually built on a foundation of continuous integration and continuous delivery, or CI/CD.
And for testing, this is a huge change. But there's a common misconception, isn't there? That DevOps means you can just automate everything and get rid of all manual testing.
That's the big myth. DevOps relies heavily on automation to manage regression risk, yes. But it absolutely does not eliminate the need for manual testing.
Why not? If your pipeline is fully automated and green, doesn't that mean the product is good to go?
It means you haven't broken existing functionality. It minimizes regression risk. But it doesn't do much for validation risk. You still need a human with domain expertise to do exploratory testing, to think like a user, to try and break the system in creative ways that the automation doesn't cover.
And what about things like system integration testing, connecting to external services?
That's another area where automation can be brittle. Those third-party APIs change without notice. A human tester is much better equipped to manage and troubleshoot those complex external dependencies.
All this change emphasizes the need to learn and adapt. The syllabus highlights the retrospective as the key mechanism for that. Retrospectives are non-negotiable in a good process. At the end of an iteration, the whole team gets together and asks, what went well, what didn't? How can we improve our process for the next cycle? For testers, this is where we refine our checklists, improve our test plans, and find better ways to collaborate with developers. Okay, let's get into the formal structure here. We need to distinguish between test levels and test types. Test levels define the scope of our testing. Right, we start at the smallest scope. Component testing, also known as unit testing. This is testing individual modules or units of code in isolation, usually done by the developer who wrote it. Then we combine them.
Yes, component integration testing, where we check the interfaces and interactions between those components.
And once the components are integrated, we move up to system testing.
This is where we look at the system as a complete, integrated whole. We're testing its end-to-end behavior against the overall system requirements. This often includes functional and non-functional testing, and it's usually where an independent test team takes the lead.
What's the difference between that and system integration testing? They sound very similar.
It's a subtle but key difference. System integration testing is focused specifically on the interfaces between your system and external systems or third-party services. Think about testing your connection to a payment gateway or an external data feed.
I see. So it's about the external boundaries. And finally, the last level is acceptance testing.
This is all about validation. It's asking, is the system ready for deployment? This is where you have user acceptance testing, UAT, where business users confirm testing, which checks things like backups and deployment procedures.
Okay, so those are the levels. Now, test types are about the objective of the test.
Right. The most common one is functional testing. This is testing what the system does. Does it meet the functional requirements? Does the button do the right thing? Is the calculation correct?
And the other side of that coin is non-functional testing,
which is about how well the system does it. Things like its performance, usability, security, reliability, compatibility. The syllabus references the ISO 2005010 standard for a full list of these characteristics.
And the big risk with non-functional testing is that these defects are often found very late in the process.
Extremely late, because you often need a fully integrated production-like environment to properly test for things like performance under load or security vulnerabilities. Finding a major performance bottleneck a week before launch is a nightmare scenario. It's another strong argument for shifting these activities left.
We can also categorize tests by viewpoint. Black box testing.
Is testing from the outside? You have no knowledge of the internal code or structure. You're just looking at the specification and testing the inputs and outputs.
And white box testing is the opposite.
You're testing from the inside. Your tests are based on the internal structure of the code, the architecture, the decision paths.
And finally, the syllabus distinguishes two critical post-change activities. First is confirmation testing.
That's when a bug has been fixed, and you run a test to confirm that the fix actually worked. It's often called retesting.
And the second is regression testing.
This is to make sure that the fix, or any other recent change, hasn't accidentally broken something else in a different part of the application. It's checking for unintended side effects. And with the speed of modern development, automating your regression suite is absolutely essential. It's not a luxury, it's a necessity.
If we agree that early testing is the most powerful principle, then that means static testing is probably the highest leverage activity a QA professional can engage in. Chapter 3 really dives into this. It's about 80 minutes of suggested training.
Yeah, this is the heart of the shift left philosophy. The main K2 objective here is to be able to compare and contrast static and dynamic testing.
Okay, so dynamic testing is what most people think of as testing. It involves actually running the software.
Right. You execute the code, and that execution can cause failures. From those failures, you have to diagnose the underlying defect.
But with static testing, you're not running anything.
Correct. You're evaluating the work products themselves, the requirements, the user stories, the design documents, the source code, without executing them. The huge advantage is that you find the defect directly.
That distinction is so important. Finding a defect directly in a requirements document is incredibly cheap and fast to fix. You avoid that whole long process of setting up an environment, reproducing a failure, and debugging.
The value proposition is just massive. Static testing finds defects in things dynamic testing can't even touch, like specification documents. It finds them earlier than dynamic testing ever could, preventing them from spawning other related defects down the line.
And it can even find certain quality issues, like poor maintainability in code, that don't necessarily cause a failure but are still very important.
Exactly. You need to be ready to give examples of defects that are easier to find statically.
So things like ambiguities or contradictions in the requirements. Or, in the code, a static analysis tool could find things like unused variables, security vulnerabilities like potential SQL injection, or code that doesn't follow the team's coding standards.
All perfect examples. You're finding the flaw before it ever has a chance to become an executing part of the application logic.
One of the most powerful forms of static testing is the review process. This is how we formalize that early feedback loop.
And that early feedback is vital because requirements are not static. The business vision drifts, stakeholders make assumptions, developers make different assumptions. Frequent reviews are the only way to keep everyone aligned and prevent the team from building the wrong thing.
It's about creating a shared understanding to prevent those big, expensive miscommunication defects.
The syllabus outlines a formal review process based on an ISO standard that has 5 main activities.
Okay, let's walk through them. It starts with planning.
Right. You define the scope, the purpose, who needs to be involved, and what your exit criteria are. Then you move to review initiation, which is just distributing the documents and making sure everyone knows their role.
Next is individual review. This is the homework part.
Yes. Each reviewer goes through the document on their own, usually with a checklist, and identifies potential issues or anomalies.
Then you have communication and analysis. This is where everyone comes together.
Well, they don't always have to have a physical meeting, but this is the stage where the findings are discussed, decisions are made on them, and they're logged.
And it all wraps up with fixing and reporting. The author makes the corrections, defects are formally logged in a tracking system, and the results of the review are documented.
And you need to know that these reviews can happen with different levels of formality. You have to be able to compare them. Let's start with the most casual one, the informal review. This is like a peer review, maybe 2 developers looking over a piece of code together. There's no formal process, no documentation. The only goal is to find some defects.
A step up from that is the walkthrough.
In a walkthrough, the author of the document leads the session. The primary goal is often to educate the reviewers and gain consensus, though finding defects is also a goal.
Then it gets more formal with the technical review.
This is led by a trained moderator, not the author, and the reviewers are technical experts. The goal is to reach consensus on technical content. You might do a technical review on a system architecture design.
And at the very top of the formality scale, we have the inspection.
Inspection is the most formal and most rigorous type. It must follow that full 5-step process we just discussed, including collecting metrics. The sole objective is to find the maximum number of anomalies possible.
And the roles are very strict, right? The author can't be the moderator.
Correct. It enforces a separation of roles to ensure objectivity.
I have to ask, though, in a really fast-paced, agile team, does a formal inspection still make sense? It sounds like it could really slow things down.
That's a great question, and it's a classic trade-off. For a simple user story, no. An inspection is total overkill. But imagine you're reviewing the design for the core security module of a banking application.
Okay, the risk is much higher there. The risk is catastrophic if you miss a defect. In that high-risk context, the time and effort of a formal, metrics-driven inspection is not only justified, it's essential. It all comes back to Principle 6. Testing is context-dependent. You choose the right level of formality for the risk you're trying to mitigate.
All right, let's get into the real heart of the syllabus. This is Chapter 4, Test Analysis and Design. The syllabus allocates a massive 390 minutes of training time here for a reason. This chapter is loaded with K3 application objectives.
So this is the difference between someone who can talk about testing and someone who can actually do testing.
That's it, exactly. This is the tester's toolkit. We'll start with the black box techniques, which are also called specification-based techniques, because they're derived from requirements, not from the code. First up is a classic, equivalence partitioning, or EP. The core idea behind EP is efficiency. We know we can't test everything, so we divide the possible inputs into partitions or groups where we expect the system to behave the same way for every value in that group.
So you only need to test one representative value from each group.
Right. You identify your valid partitions, the data the system should accept, and your invalid partitions, the data it should reject. For 100% EP coverage, you just need one test case for each partition you've identified.
But we know that a lot of bugs happen right at the edges of those partitions. So that's where boundary value analysis, or BVA, comes in.
Exactly. BVA is a refinement of EP that focuses specifically on those boundaries, because that's where developers are most likely to make off-by-one errors.
Let's use a concrete K3 example to make this real. Imagine an input field for an order quantity that must be between 10 and 99 inclusive. Okay, so our valid partition is 10.99. We have two invalid partitions, anything less than 10 and anything greater than 99. The syllabus talks about two-value BVA. What test cases would that give us for this example?
With two-value BVA, you test the boundary value itself and its closest neighbor in the adjacent partition. So for the lower boundary of 10, we test 10 on the boundary and 9, the invalid neighbor.
And for the upper boundary of 99, we test 99 and its neighbor, 100.
Correct. So our four boundary test cases are 9, 10, 99, and 100. Simple and effective.
But then there's a more rigorous three-value BVA. What's the point of the extra test, and what does it look like here?
The point is to catch even more subtle boundary errors. Like if a developer wrote 9 instead of a 1010. With three-value BVA, you test the boundary itself, the value just below it, and the value just above it.
So for a boundary of 10, we'd test 9, 10, and 11.
And for the upper boundary of 99, we'd test 98, 99, and 100. So our full set of tests becomes 9, 10, 11, 98, 99, and 100. It's more thorough and gives you higher confidence.
Okay, moving on from numerical inputs to complex business rules. That's where decision table testing comes in.
Yes, this is an incredibly powerful technique when you have logic that depends on multiple conditions being true or false. A decision table helps you systematically consider every possible combination.
So you structure it with the conditions as rows, the actions as another set of rows, and then each column is a rule that represents a unique combination of conditions.
Exactly. And the real power comes from the fact that it forces you to think through all combinations, which often reveals gaps or contradictions in the original requirements document. Your coverage goal here is to have one test case for each feasible rule in the table.
And the last major black box technique is state transition testing.
This is perfect for testing systems that have a defined workflow or move through different states, like an online shopping cart or an ATM machine. You model the system with states, events that trigger changes, and the transitions between states.
And there are different levels of coverage here, too.
Yes. The weakest is just all states coverage, making sure you visited every state at least once. The most common and practical is valid transitions coverage, also called zero-switch coverage, where you exercise every valid transition on the diagram.
And for high-risk systems, there's a stronger level.
Right. All transitions coverage. This requires you to test all the valid transitions, plus you must try to trigger all the identified invalid transitions to make sure the system handles them gracefully and doesn't crash. Now let's shift gears to the white box techniques. Remember, these are structure-based. You're designing tests based on your knowledge of the code itself. Testers need to understand the concepts, even if developers are the ones doing it.
The two big ones here are about code coverage. Let's start with statement testing.
This is the most basic form of coverage. The coverage item is an executable line of code. So 100% statement coverage simply means that every single executable line in the program has been run at least once by your test suite.
But that sounds like it could miss a lot.
It does. 100% statement coverage is actually quite weak. It doesn't guarantee you've tested all the decision logic. That's why we have branch testing.
So here the coverage item is a branch, which is the outcome of a decision point in the code, like an if statement having a true path and a false path.
Exactly. To get 100% branch coverage, you must have test cases that execute both the true and the false outcome for every decision in the code. And this is a key point for the exam. 100% branch coverage always implies 100% statement coverage. Always. You can't test every branch without also executing every statement within those branches. The reverse is not true, though.
So what's the real value of measuring this?
It gives you an objective, quantifiable metric of how much of the code your tests have actually touched. It can highlight areas of the code that are completely untested.
But it has a fundamental weakness, right? The syllabus mentions defects of omission.
A huge weakness. White box testing can only tell you about the code that is there. If a developer completely forgot to implement a critical requirement, white box testing will never find it because there's no code to test. That's why you need a combination of black box, white box, and static testing.
So beyond those formal techniques, the syllabus also covers experience-based methods.
Yes, these are less formal
Huh.
and rely heavily on the skill and intuition of the tester. The classic one is error guessing.
This is where you use your experience to anticipate where the bugs are likely to be. Developers often struggle with things like date handling or null pointers, so you target those areas.
Right. A more structured version of this is a fault attack, where you use a predefined list or checklist of common failure types and methodically try to trigger them.
Then there's exploratory testing.
This is a really powerful one. It's simultaneous learning, test design, and test execution. You're exploring the application and designing and running tests on the fly as you learn more about it. It's often structured into time-boxed sessions with a specific goal called a test charter.
And finally, checklist-based testing, which is pretty self-explanatory. You use a high-level checklist to guide your testing.
The key here is that the checklist must be a living document. You have to keep updating it based on the new defects you find in production.
The last part of this big chapter is about collaborative approaches, which is huge in Agile. We touched on collaborative user story rating earlier.
Right, the 3 C's card: conversation and confirmation. The important part for testing is the confirmation, which is defined by the acceptance criteria.
And those criteria become the basis for our acceptance tests. They can be written in a scenario-oriented format, like given when then, or a simpler rule-oriented format, like a bulleted list.
And this all culminates in the K3 objective of using ATDD to derive test cases. This brings everything together.
Walk me through that process.
You start with a specification workshop with the whole team. You analyze the acceptance criteria until everyone agrees on them and they meet the INVEST criteria: independent, negotiable, valuable, etc. Then you write the test cases right there in the meeting.
And you start with the positive paths first, then negative, then non-functional.
That's the typical flow. And the critical final step is that when those test cases are automated, they become the executable specification. The developer's job is to write code until those tests pass. It completely reframes the development process. All right, that was a massive chapter. Let's move on to the more strategic side of things with Chapter 5. Managing the test activities. This is another big one, 335 minutes of training. This chapter is all about organization, planning, and risk. The anchor for all of this is the test plan.
You have to have a documented plan. It's not just for the testers. It's a communication tool for the entire project to tell stakeholders what you're doing, how you're doing it, and why.
Mm-hmm. And a key part of that plan is defining your entry criteria and exit criteria. This is a K2 comparison you need to know.
Entry criteria are the prerequisites, the things that must be true before you can start a tapping activity. Like, is the test environment stable? Are the user stories ready for testing?
And if you start testing before those criteria are met, you're just introducing risk and inefficiency into the process.
And exit criteria are the opposite. They define when you're done.
Exactly. What conditions must be met to say this phase of testing is complete? Maybe it's reaching 95% requirements coverage, or executing all planned tests, or having no outstanding critical defects. In Agile, these map pretty directly to the definition of ready and definition of done. Now we get to another major K3 area: estimation techniques. This is always a challenge. Always. The syllabus gives us 4 main ways to approach it. The first is metrics-based, estimation based on ratios.
This is where you use historical data from your organization. If you know that, on average, testing takes about 30% of the total development effort, you can apply that ratio to the estimate for the current project.
It's simple, but it's only as good as your historical data. The second technique is extrapolation. This works well in iterative models.
So you measure your team's velocity in the first few sprints, and then you use that trend to project how much longer the rest of the work will take. Right. The third is an expert-based consensus approach, wideband Delphi, or, in Agile, planning poker. This is where the team members all provide individual anonymous estimates, and then they discuss the differences and re-estimate until they converge on a number the whole team can agree on. It's great for mitigating individual biases and getting team buy-in. And finally, we have the one you might have to actually calculate on the exam, 3-point estimation. This is where you account for uncertainty by providing 3 numbers: an optimistic estimate, A, a most likely estimate, M, and a pessimistic estimate, B.
And the formula for the weighted average, E, is A plus 4 meter plus B, 6. The M is weighted 4 times heavier because it's the most likely outcome.
So let's do a quick example. If A is 6 hours, M is 12 hours, and B is 24 hours.
Okay, so E equals 6 plus 4, 12, plus 24, 6. That's 6 plus 48 plus 24, 6, which is 78, 6. So your calculated estimate is 13 hours. It's a much more risk-aware way of estimating. Once we have our tests, we need to prioritize them. This is another K3 application skill, test case prioritization. You can never run all your tests all the time, so you have to be smart about the order. The most important strategy is risk-based prioritization. You run the tests that cover the highest risk features first.
You could also do coverage-based prioritization, like ordering your tests to achieve 100% branch coverage as quickly as possible.
Or requirements-based prioritization, where you simply follow the priorities set by the business stakeholders. The key is to have a deliberate strategy,
The syllabus also brings in two key visualization models here: the test pyramid.
which is a strategy for test automation. It says you should have a huge base of fast, cheap, isolated unit tests,
Yep.
then a smaller layer of integration tests, and at the very top, a tiny number of slow, expensive end-to-end UI tests. You want to push testing as far down the pyramid as possible.
And the second model is the testing quadrants. This is a conceptual model that helps teams think about what types of testing they need. It maps test types on two axes: business-facing versus technology-facing, and tests that support the team versus tests that critique the product. It's a way to ensure you have a balanced testing strategy. Okay, this all leads to the absolute core of test management: risk management. This is the backbone of being a professional tester. A risk is defined by two things: its risk likelihood, the probability of it happening, and its risk impact, the severity of the consequences if it does. Together, they give you the risk level. And we have to be able to distinguish between two main types of risks. First, project risks.
These are risks related to the management of the project itself, things that could threaten the schedule, budget, or scope.
Like key staff members getting sick, or the customer constantly changing the requirements scope creep.
Exactly. These are things that a project manager worries about. The other type is product risks.
These are the risks related to the quality of the software itself, the potential for defects to exist in the final product.
Right. This is the tester's domain. A product risk could be the system might not be able to handle our peak holiday traffic, which is a performance risk. Or a hacker might be able to access customer data, a security risk.
And product risk analysis is what drives our entire test strategy.
It has to. You identify the product risks, you assess their likelihood and impact, and you prioritize them. That prioritized list tells you exactly where to focus your testing effort. You spend the most time and use the most rigorous techniques on the highest risk areas of the application.
And the actions you take in response are called product risk control.
And testing is the primary control measure. So control action might be assigning your most experienced tester to a high-risk module, or requiring a formal inspection for a critical component, or mandating 100% branch coverage for a security-sensitive piece of code.
Once testing starts, we move into the monitoring and reporting loop.
Right. We use test metrics to monitor progress, things like the percentage of tests executed, the pass-fail rate, defect density, and requirements coverage.
And we communicate this progress using reports. We have the ongoing test progress reports,
Which are regular updates for stakeholders on status, progress against the plan, and any blocking issues. And then at the end, we have the final test completion report.
This summarizes the entire test effort, gives a final assessment of product quality against the exit criteria, documents lessons learned, and, crucially, lists any remaining unmitigated risks that the business has decided to accept.
And of course, during execution, we're finding defects, which requires proper defect management. Being able to write a good defect report is a K3 skill.
So what are the essential elements?
You need a unique ID and a clear, concise title. You need to identify the test environment and the version of the software. You need precise, step-by-step instructions on how to reproduce the failure.
And you need to show the expected result versus the actual result.
Crucially, yes. And finally, you need to classify it with severity. How bad is the impact on the user or the business? And a priority. How urgently does this need to be fixed?
And those two things are not the same. You could have a low-severity cosmetic bug, like a typo, that's high priority because it's on the homepage and looks unprofessional.
Exactly. Or a high-severity data corruption bug that's low priority because it only happens on a very obscure old operating system that almost no one uses. That distinction is key. All right, that brings us to our final and shortest chapter. Chapter 6 is all about test tools. It's only about 20 minutes of material, but in the real world, you can't be an effective tester without them.
The syllabus groups the tools by the testing activity they support. So you have management tools for things like Jira or Azure DevOps for tracking requirements and defects.
Right. Then you have static testing tools like static code analyzers. You have test design tools that can help generate test data.
And then the big category of execution tools.
Yeah, your test execution tools for running automated scripts, your coverage tools for measuring code coverage, and your specialized non-functional testing tools for performance, load, and security testing.
The exam requires you to be able to recall the benefits and risks of test automation. Let's start with the good stuff, the benefits.
The number one benefit is saving a massive amount of time on repetitive work, especially regression testing. Automation gives you consistency, repeatability, and much faster feedback to developers.
And it frees up the human testers to do more valuable things.
Exactly. It lets them focus on the hard stuff, complex test design, exploratory testing, the things that require human creativity and critical thinking.
But it's not a silver bullet. There are significant risks involved.
The biggest risk is probably unrealistic expectations. People think they can just buy a tool and fire all their manual testers, and it just doesn't work that way.
And there's a huge underestimation of the effort involved.
A huge one. The initial setup is a project in itself. And more importantly, the ongoing maintenance of the automated scripts is a major effort. Test automation is software development. If you don't maintain your test code, it will become brittle, unreliable, and eventually useless.
There's also the risk of over-relying on it and forgetting that you still need that human critical thinking element.
For sure, automation is a powerful tool, but it's just one tool in the overall quality assurance toolkit.
So we have made it through the entire ISTQB CTFL v4.0 syllabus. We've gone from the fundamentals of the failure chain and the 7 principles, all the way to the strategic application of K3 techniques like boundary value analysis and risk-based management.
And hopefully it's clear that mastering this isn't just about memorizing terms, it's about understanding the why. Why we have these principles, why collaboration is so critical in ATDD, and why risk must be the engine that drives everything we do as testers.
And we have to remember that crucial limitation we talked about. White box testing can give us great confidence in the code that's been written, but it is completely blind to defects of omission. It can't find the requirements that were never coded in the first place.
Which can only be caught by really robust static testing reviews and analysis right at the beginning of the process.
And that brings us to our final provocative thought for you to take away from this deep dive.
If the success of your entire project really hinges on doing robust risk analysis early, and if your code coverage metrics can't see the features that were completely missed, then how often are you formally tracking your residual product risk after you ship? And are you absolutely certain your risk analysis covered the requirements that were never written down, but were just assumed by everyone to be part of the system?
The future of quality assurance is really about strategic risk mitigation. Focus on that K3 application, get hands-on practice with these techniques, and you will not only secure the certification, but immediately become a more valuable professional.
We wish you the absolute best in your preparation journey.
And thank you for taking this deep dive with us. We'll see you next time.